Welcome to Information Theory Frontiers, where we explore recent advances in network dynamics, coding, and communication. In today's episode, we present a synthesis of cutting-edge research published on April 25, 2025. We'll be exploring breakthroughs in information freshness, error correction, and secure communication, while examining new paradigms that challenge established theoretical limits. Join us as we navigate through the latest developments that are reshaping our understanding of how information works in increasingly complex systems. Let's begin with a brief overview of information theory, the mathematical foundation of modern digital systems. Information theory originated with Claude Shannon in the 1940s, providing a framework for quantifying information storage and communication. This field establishes fundamental limits for data compression, transmission, and error correction that cannot be surpassed regardless of technological advances. Information theory underpins all digital communications, from internet protocols to wireless networks that we rely on daily. Increasingly, its principles influence emerging fields such as quantum computing, machine learning, and biological data systems. Today's research continues to push boundaries in privacy, network dynamics, and specialized channels, demonstrating the field's ongoing vitality and relevance in our data-driven world. Our first research theme focuses on network information dynamics, moving beyond static networks to understand information freshness. Shrivastava and colleagues have introduced a groundbreaking framework for analyzing information freshness in dynamic gossip networks. They utilize the version age of information metric to quantify staleness in time-varying network topologies. Their key finding reveals that rapid network topology transitions can achieve the performance of the best configuration, even when that configuration isn't maintained continuously. This research has direct applications in sensor networks, Internet of Things systems, and mobile ad hoc networks where connections constantly change. Perhaps most importantly, this work challenges conventional static network analysis by introducing dynamic modeling approaches that better reflect real-world conditions where network connections are rarely fixed. The second research theme examines advanced coding techniques, focusing on error correction and efficient storage solutions. Arno and colleagues have developed generalized bicycle codes for quantum error correction, while Zhao and team have introduced rack-aware minimum storage regenerating codes for distributed systems. Both approaches achieve significantly better performance with fewer resources, whether those are qubits in quantum computing or storage units in data centers. These advances have applications spanning from quantum computing to large-scale data centers where efficiency and reliability are paramount. What makes these advances possible are sophisticated mathematical structures, including circulant matrices and algebraic constructions, demonstrating how abstract mathematics translates into practical improvements in computing infrastructure. Our third research theme explores privacy-preserving communication, addressing the critical balance between efficiency and user privacy. Liu and colleagues have characterized optimal memory rate trade-offs in demand private coded caching, establishing exactly how much efficiency must be sacrificed to maintain privacy. Meanwhile, Dinesen and team have extended secret sharing to the rank metric, enhancing fundamental cryptographic primitives. Both works establish fundamental limits on private information exchange, creating theoretical boundaries that no system can exceed. These findings have direct applications in content delivery networks and secure distributed computing environments. Information theory provides a rigorous framework for quantifying these privacy performance trade-offs, allowing system designers to make informed decisions about implementation trade-offs. The fourth research theme highlights novel communication paradigms that break conventional barriers. In a particularly significant development, Ivanov and colleagues demonstrate that MIMO probabilistic shaping can exceed the 1.53 decibels AWGN gain limit, challenging what was previously thought to be a fundamental barrier. Xu and team introduce hybrid active-passive communications for symbiotic radio systems, creating new possibilities for low-power devices. Meanwhile, Tamir and colleagues analyze frequency-based channels with unlimited resolution for DNA storage applications. These approaches collectively challenge traditional communication models and theoretical limits that have guided the field for decades. They represent cross-disciplinary applications that extend information theory principles to entirely new domains, from molecular storage to next-generation wireless systems. Looking across all 9 papers, several key findings emerge with potentially broad impact. Most notably, Ivanov and colleagues break the 1.53 decibels barrier by achieving more than 2 decibels gains in MIMO systems, challenging a long-established theoretical limit. In network dynamics, Shrivastava and team demonstrate that fast-switching networks can match the performance of the best topology, even when that topology is only intermittently available. Liu and colleagues characterize optimal memory rate trade-offs for private caching, establishing fundamental limits for privacy-preserving content delivery. On the mathematical front, Meharry and team provide explicit Hamiltonian decompositions for all uniform hypergraphs, solving a long-standing theoretical problem. Finally, we see successful cross-domain extension of information theory principles to areas like DNA storage and Internet of Things applications, demonstrating the field's versatility. Several common methodologies drive advances across these information theory research papers. First, researchers employ information theoretic bounds, establishing fundamental limits and then developing schemes to approach them. Second, mathematical structures play a crucial role, with researchers leveraging algebraic constructions and combinatorial designs to create elegant solutions. Third, Markov models appear frequently, capturing dynamic, probabilistic system behavior with rigorous mathematical analysis. Fourth, cross-disciplinary applications extend information theory to new domains, from biology to quantum computing. Finally, optimization techniques for resource allocation appear throughout the literature, addressing challenges in caching, bandwidth management, and communication efficiency. These methodological approaches collectively demonstrate how information theory combines theoretical rigor with practical application. Let's examine our first seminal paper in greater depth. Information Freshness in Dynamic Networks by Shrivastava and colleagues. This work introduces the first comprehensive framework for analyzing information freshness in networks with time-varying topologies. Their key insight reveals that switching between network topologies faster than a threshold related to the better performing topology enables the system to achieve the performance of that best topology. The researchers introduce the concept of a typical set to focus analysis on nodes that most significantly impact overall performance. This research has direct applications in vehicular networks, mobile ad hoc networks, and Internet of Things deployments where connections are inherently dynamic. The significance of this work lies in providing a mathematical foundation for designing networks that maintain information freshness despite constantly changing connection patterns. Our second seminal paper, Breaking the 1.53 decibels barrier in MIMO systems by Ivanov and colleagues, challenges a well-established limit in communication theory. The researchers achieve more than 2 decibels gains using a nonlinear sphere decoding demapper in multiple input multiple output systems, exceeding what was previously considered a fundamental barrier. Their key insight reveals that in MIMO systems, both signal and interference are shaped, enabling performance that goes beyond theoretical limits established for simpler channel models. The significance of this work cannot be overstated. It could improve data rates, reliability, and coverage in wireless networks that form the backbone of our connected world. This research demonstrates the importance of considering the entire communication system, including receiver algorithms, when analyzing fundamental performance limits. The third seminal paper we'll examine is Demand Private Coded Caching by Liu and colleagues, which addresses the critical challenge of efficient content delivery while preserving request privacy. The researchers characterize optimal memory rate trade-offs for small cache sizes, establishing exactly how system resources should be allocated. They solve previously open cases, including when the number of files is less than or equal to the number of users, and the special case of 2 files with any number of users. To achieve these results, the team develops novel proof techniques combining information theory and combinatorial methods. The significance of this work lies in establishing theoretical limits for privacy-preserving content delivery networks, providing a foundation for designing systems that balance performance with privacy protection. Looking toward the future, several promising research directions emerge from these papers. In dynamic network information theory, researchers will likely explore more complex models with multiple topologies and diverse information dissemination strategies. For beyond-limit communication, extending the MIMO insights to multi-user scenarios and other channel types presents exciting opportunities. In the realm of privacy-performance trade-offs, developing practical implementations of theoretical schemes will be crucial for real-world deployment. Biological information channels, particularly DNA storage and molecular communication, represent a frontier where information theory principles are just beginning to be applied. Finally, cross-disciplinary applications continue to expand, with information theory increasingly influencing machine learning, quantum systems, and other fields where information processing is fundamental. As we conclude our exploration of information theory frontiers, several key themes emerge. Information theory continues to break established limits, as demonstrated by Ivanov and colleagues exceeding the 1.53 decibels barrier in MIMO systems. Dynamic systems with changing topologies require new analytical frameworks, as shown in Srivastava's work on information freshness. Privacy and security constraints are being formalized within information theory by Liu and others, establishing rigorous foundations for secure communication. Cross-disciplinary applications extend information theory's impact far beyond its traditional domains, from biological storage to quantum computing. Through all these advances, mathematical foundations remain central to progress across all information theory subfields, demonstrating the enduring power of rigorous mathematical analysis in solving complex real-world problems. This research synthesis was created using advanced AI tools to bring you the latest developments in information theory. The content generation was powered by GPT, Anthropic Claude 3-7 Sonnet 20250219, with text-to-speech synthesis provided by Google TTS technology. Visual elements were created using the Grok AI visualization system. All generated content was carefully reviewed and validated by human information theory experts to ensure accuracy and relevance. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from ArXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.